Now, temperatures and blackbodies. A blackbody is an imaginary construct. It is something thought of in a mathematical sense and a physical sense. But in terms of practical applications here, you can think of it as something that emits radiation thermally as opposed to non-thermally. So anything that is warm, you can think of as a blackbody. So that means that you are a blackbody. So are the heating elements in your toaster. So are in old-fashioned light bulbs that have the element that glows, not the fluorescent bulbs, but the traditional light bulbs. Those are also blackbodies. And that, incidentally, is why those old kind of light bulbs are phased out, because in order to heat them up enough to glow in the optical, they put out a phenomenal amount of infrared light, which is wasted energy. That's why it's better to use the fluorescent lights rather than the old, or LEDs rather than the old kind of light bulbs. But I digress. We can approximate stars as black bodies. Stars are not really black bodies, but in many applications we can fake it, especially at the longest bands of light, infrared and radio. Or, well, infrared and submillimeter at least. Sometimes we can approximate dusty disks as additional black bodies. You can have a black body for the star and a second black body for the dust around it. And just as a reminder, remember that the words SED and blackbody are not interchangeable. The SED is a spectral energy distribution, and you can plot the observed brightnesses, converted into the appropriate units, on an SED. A blackbody is a specific mathematical relationship, and you can fit a blackbody to an SED. You can fit more than one blackbody to an SED. Not all SEDs are blackbodies. You can plot a blackbody on an SED. Does that make sense? Okay. Now, you may have seen this kind of slide in earlier movies or images like the top two in Astro 101 textbooks. These two pictures I've grabbed here are from two different astronomy textbooks, and they have, one on the left has intensity as a function of wavelength. This one says it's power as a function of wavelength. When we encounter black bodies, it's going to be in the context of spectral energy distribution. So we're going to talk about it as spectral energy as a function of wavelength. Interestingly, they've given, both of these have no units on the y-axis at all. On the x-axis, they've given linear wavelength, which is a little peculiar, but okay. We're going to definitely plot things in the log on both axes. The y-axis is going to be in the log, and so is the x-axis in wavelength. In these two plots, in both cases, we've got these somewhat funky looking curves. These curves are blackbody curves, and they are specified in terms of temperature. So when you pick a temperature, you can calculate the intensity as a function of wavelength, uniquely for that temperature. So in both of these cases, they're both using the same mathematical expression, but they're showing you slightly different things. They've put visible light here where they've got one peak to the blue of the visible light, one peak in the visible light, and one peak to the red of the visible light. In this plot, they've got visible light to the left of all of their example blackbody curves. And look at the temperatures. This one is 2,000 Kelvin. Their hottest one is 2,000 Kelvin. Here, their coolest one is 3,000 Kelvin, right? The 3,000 Kelvin one here, the peak is redward of visible. 2,000 Kelvin, the peak is redward of visible. Those things are related. So when we encounter black bodies, we're going to plot them like this. So there's, in this case, spectral energy in log on the y-axis and wavelength in log on the x-axis. And this side is called the Wien side because it was mathematically described first by somebody by the name of Wien. And this side is called the Rayleigh-Jeans side because it was first mathematically described by two different people, one by the name of Rayleigh and one by the name of Jeans. And this was both done in the late 1800s, early 1900s. And it was very confusing to physicists for a long time trying to tie together this side of this curve and this side of this curve. And so it took them a long time to come up with a mathematical expression that unified this, that described all of this together. And that hideous mathematical expression are both of these. Both of these are the Blackbody equation. This one is a Blackbody equation in terms of wavelength and temperature. This one is a Blackbody equation in terms of frequency and temperature. Okay, so K is the Boltzmann constant, H is the Planck constant, C is the speed of light, nu is the frequency of light, lambda is the wavelength of light, and T is temperature of the emitting object, and E is that mathematical constant, 2.718, and so on. Okay? So hopefully you've gotten the idea here of all of the constants. So this hairy math reduces in log space to that shape that was on this shape here. And if that shape isn't familiar yet, it will be. You can calculate this function either as a function of wavelength or a frequency. And the shape of it is slightly different depending on whether you do it as a function of wavelength or frequency, depending on which parameter space you're in. So I think in terms of wavelength, so all of the SEDs I'm going to show you are in terms of wavelength. So here I have a movie. What this movie is, so on the y-axis, we've got log of lambda f lambda. So it's a spectral energy distribution, so that's energy density in the log. The x-axis is the log of the wavelength in microns. Okay, so it's a log-log plot. All I'm doing here is calculating that Blackbody equation as a function of wavelength for a variety of different temperatures. And the temperatures are what's given in the upper right. And those temperatures are temperatures corresponding to the spectral types that are given underneath it. So I've just pulled those out of a table of spectral types and effective temperatures. So those are approximations to the brightnesses that you'd expect for, not the brightnesses, sorry, the shape of the spectral energy distribution that you'd expect for stars of those spectral types. Those vertical dotted lines are located at the positions of several different common filters. I've got some optical filters in here, U, B, and V, Johnson, U, B, and V. R prime, that's coming from IFAS, cousins I. I haven't put in all of the dotted lines. I think the dotted line is there for B and for R, maybe. Might be for B and V, I'm not sure anymore. But the point is that the optical stuff is near here. Then J, H, and K from 2MASS is in here. Then we've got the IRAC 4 filters, and then we've got Ys and MIPS 24, 70, 160, 250, and 500 from Herschel is out there. Okay, so look and see here. The overall brightness is increasing. Not just the shape is changing, but the overall brightness is increasing as temperature is increasing. So the whole thing's getting brighter, not just the shape, but the whole thing is getting brighter as the temperature increases. The next thing to notice is that peak moves bluer as the temperature increases. The coolest thing I've got there is an M8 star at 2600 Kelvin. And the brightest thing I've got there is an O something. Let's see what it is. An O3 at 52,000 Kelvin. So the peak moves bluer as the temperature increases. The other thing to note is starting about there, so like A stars and later, all of the optical filters are either on the peak or on the Wien side of the curve. The optical and near IR filters are generally straddling the peak of this function. And as for most of these, when you get into the O stars, things are a little bit different. But for B through M, the slope of this line through those optical filters changes tremendously. For O stars, the black line is pointing down. For the M stars, it's pointing up. So there's huge changes going through there. Remember that colors are flux ratios. So when I take the optical colors, like B minus V, for most of these star-like temperatures, I can map B minus V colors uniquely to temperature. That's how come it works. It starts to fail for really, really, really bright stars like early O stars. But for most of the stars in this collection, I can take the B minus V color and get a temperature out. But look at the infrared side, the IRAC through Herschel. That slope doesn't change through all of these stars. It might be starting to change a little bit by the time we get to M8, but only for the shortest Iraq. The whole thing goes up and down, but the slope doesn't change. So the IR colors are 0 for stars that don't have dust around them. So for anything that doesn't have 0 infrared color, they must not have this SED shape. Look at that. We've already learned something. We've figured out that infrared colors that are not 0 are going to tell us about things that don't look like stars without dust. That's going to be a really powerful thing. However, if you have objects for which you only have points on the Rayleigh-Jean side of the SED, you can tell some things about the source, but having points on the Veen side of the SED help us a lot, because it helps us figure out what the complete SED shape is, and helps us constrain, even whether or not it's a star at all, helps us constrain what the temperature of the star is. And then we've got reddening, which is another complication we'll get to in a minute. Okay? Have you ever wondered why the term is effective temperature, or T sub EFF, or T effective, rather than just temperature? It's because we are approximating the stars as black bodies. They're not black bodies, but they're close. So T effective, or effective temperature, is the temperature of the black body that approximates the stellar emission, hence effective. Now, reddening. Reddening is an additional complication. So this movie is the same kind of family of things as we were just looking at, but now, rather than changing temperature, I'm holding the temperature constant. This is a G-star, 5800 Kelvin blackbody. So it's a G-star just like our sun, and I'm holding the temperature constant. But what I'm changing is the reddening. Like reddened sunsets, stars are going to get reddened. The light from stars or galaxies or anything gets reddened by dust grains in the interstellar medium or in our solar system. Any dust grains between us and the source of light is going to scatter the blue light out, just like in a reddened sunset. So it's going to scatter the blue light out. It's going to redden the light. So this 5800 Kelvin blackbody in the simulation I've got going here, what I'm changing, what I'm cranking up and down, is the amount of dust in between us and this 58 Kelvin blackbody. And what's written down in the upper right is the amount of reddening in magnitudes in J-band, because that's what my code takes. And then I've converted it to reddening in V-band optical below it. So when the movie runs, you can see that I can dial up the J-band extinction a little bit, and the V-band magnitude extinction goes up a lot. That's because it matters more at shorter wavelengths, because it affects the shorter wavelengths more. Look at how that SED, look at how the SED changes as I crank up the extinction. The blue side of the SED gets pulled down really fast. Boom! It gets pulled down really fast. And it takes much more reddening to pull down the rest of it. That big notch, that's an absorption line. That's a silicate absorption line. It's a big honkin' 10 micron absorption line from silicates in the dust. But you have to get to a really ridiculously high reddening before you start to notice an effect at IRAC bands. And you pretty much don't ever notice much of anything out here, because it doesn't matter. Here it's starting to matter, but you already got 12, 15 magnitudes of extinction at AV before you start to notice. So here again, if all you have is photometry for a given source, it is really hard to tell if what you have is a low mass star with no extinction, or a high mass star with lots of extinction. So you have to be careful, and you have to use all of the data that you can find. The reddening is also going to change the position of objects in the color magnitude diagrams as well. We'll get to that in a little bit. But given careful and judicious use of colors, in other words, flux ratios, you can get an educated guess as to whether or not it's a high mass star with lots of reddening or a low mass. All right, so takeaway points pretty much is this movie on repeat. all of the really important things that you can tell from watching this movie on repeat. So when we get to the next steps here, spectral energy distributions and color and color magnitude diagrams, they're sort of two different facets of this giant metaphorical data cube that handles all the information for our targets. Spectral energy distributions allow you to see many wavelength points at once, but for just one object at a time. Color and color magnitude diagrams are really, really useful. They have many objects that you can see at once, but you can just use between 2 and 4 wavelengths at a time. Both ways of looking at the information are super useful, and both of them are in entirely different units. One is going to be in magnitudes, and the other is going to be in energy density. We're going to use them both because they're both really important. Points that are outliers in the SED will also make that object an outlier in a color magnitude diagram or a color diagram. Points that are missing from the spectral energy distribution means that you won't be able to place that object in its corresponding color magnitude diagram, because if we don't have the point, then we can't, of course, plot it in that diagram.